starts.
Well, yeah, but also when I came in just a few minutes ago, the sign up front was still wrong.
That's it. Okay. Oh, it's 3:30. Shall we start? Oh,
Yep.
sorry, 2:30.
Let's start. It's 11:30 on my laptop.
Yeah. Okay. Yeah, you've got a correct clock. Oh crap! Just take my phone out. Okay, it's 9:30, so we'll start promptly because the agenda is full, and we'll let people slowly shift in with their coffee. So hi everybody, this is the QIRG meeting, the Quantum Engineering Research Group. And as usual, I will start with the IETF Note 12. So I'm just gonna click through the slides slowly so that you can all absorb them.
I can read it that quickly.
And as usual, I'll just make a remark, which has already been made at several other meetings at this IETF, is that the IETF conducts research, is not a standards development organization, so we just talk about what we find interesting. Okay, as a reminder, this has already been said before, but this session is being recorded. Those of you in the room, please make sure to register with Meet Echo via the QR code. Those joining online, you're already set. And as a reminder, if switch on your video and audio only if you're presenting. Here's some tips from Rodney about how to join online, but I guess if you're here in the meeting, you've already gone through these steps.
People who are here in the room might want to use the online tool on their laptop or on their phone, and we will try to run the Q&A through the usual queue in the Meet ecosystem. So it is a big help if you can use it.
Okay. Okay, and a few slides from the chairs. Welcome everybody. This is a QIRG meeting at the IETF 122 at Bangkok. The agenda for today is actually quite packed, although each item has about 20 to 30 minutes. We'll have a few, it's all talks except the last update from Diego, which is an update on his draft, the multiplane architecture. That draft is the only one currently in work as an internet draft. As of the end of February, it's on version 3. So if you're curious what's in it, you can still have time to look it up. And actually, that's it for the chair slides. And our first speaker is Rodney, without his chair hat.
All right, good morning. So while Wojtek's bringing up the slides here and handing me the clicker, we put me first so that there would be a little a chance for people to come in, and it's okay if people miss the chair's presentation because they were running late this morning. But I'm going to talk actually about some technical stuff. So this is my personal technical contribution, not chair stuff. Let's see, and the clicker works correctly. Yes. So I'm going to tell you about a recent result in particular from our lab. Most of what we have talked about.
One more thing before I've set a timer. This includes your Q&A.
Okay, thank you. I see it. Most of what we have talked about in the QIRG since the founding of QIRG is about what we sort of assumed would be wide area networking, but in fact, the area where quantum networking involving entanglement is most likely to be first really deployed in the real world is to connect together smaller quantum computers to build one larger system inside a multi-computer or a data center size thing. And that's what we're actually working on in the research groups that I'm part of. So I'm going to show you a little bit about those results today. So this is, over the last 20 years now, I've worked with a whole bunch of people, and this is just the quantum networking people, not the quantum computing people. The people whose names are highlighted there are authors on this particular paper, and the three who are in color there are the co-first authors of this particular paper. So you all probably know supercomputers like this. We want to build something like this using this, right? And it's a little different, right? So how are we going to get from this to something like this? That's part of the tale for today. So first, I want to give you a very rough look at what we believe is the necessary roadmap for the evolution of large-scale quantum computers, and then ultimately why multi-computer interconnects and/or data center scaled networks are ultimately necessary. So in the beginning, of course, there were early demonstrations of individual single qubit, single quantum bit devices going back to the 1990s. Of course, we want to have more and more of those as we go, and we want them to be higher quality or higher fidelity as we go. So we need to get from someplace down here in the lower left to someplace in the upper right. Several years ago, Professor John Preskill of Caltech introduced the term NISQ, Noisy Intermediate Scale Quantum Systems. And today we are roughly at the level of the first fault-tolerant demonstrations over the last year or so involving error correction to improve the fidelity. And of course, bigger and bigger systems continue to be built, still at sort of the noisy state of things. But soon we will reach this point as we increase the code distance or the strength of the error correcting codes we do, we'll reach the point where we reach the maximum number of physical qubits you can fit into one device. I call that max SQ, the max single chip fault tolerant quantum system. And then the question is, what do you do? What do you do when you go from there? Because the physical density of these devices, and perhaps a little bit counterintuitively since we're talking about quantum stuff, these devices are actually very, very large compared to individual transistors. And so a single chip or a single device will hold tens to thousands of physical qubits compared to the billions of transistors in a single chip. And so what do you do when you hit that limit? Well, it means we're going to have interconnects of some sort, and we'll ultimately have what I call the fault-tolerant quantum multi-computer, and that's where we're headed. So just a little bit of background. The ideas for this originated, it's a fairly obvious idea to take multiple quantum computers and tie them together using some network in order to scale things up. The first proposal, as far as I can recall, was actually Jungsang Kim's in 2005, which was also at the same time that I was doing my own PhD work on this particular topic. And I published papers on this starting in 2005 and 2006. With various collaborators, and you can see some of the other work from there. Spanning about the first decade, about from 2005 to 2015, various and sundry designs were proposed. And then between 2015 and about 2022, there was kind of a gap, kind of a lull in the work on these multi-computer systems as people focused on those NISQ systems I was talking about earlier, the smaller individual scale systems, starting to actually build those up. But then starting in 2022, there was a series of new papers, and there's been a huge burst of work on this over the last 2 years or so, 2023 and 2024, from a variety of organizations around the world, including there on the right. The one on the right is our QFly, and that's the thing I'm going to talk about. So when you want to design a system like this, I'm a systems engineer. I'm not a physicist, and so I ask questions about how big does the system need to be, how strong does it need to be, how fast does it need to be, what's the fidelity of the system need to be, how are you actually going to put this thing together? And so it results in a whole bunch of engineering-related questions. So first, let me talk about a couple of these here, the quantum error correction construction. So just like in classical computing, you have multiple you have more physical qubits or more representing a smaller number of logical qubits. And so the question is, how do you actually construct those? And the other question is, how are we actually going to execute operations between these two nodes? So that second question first. When we talk about doing a computation between two nodes in the system, we use an approach that's called a remote gate. And so what you do is you can see on the left side of the figure here, a squiggly line. That represents quantum entanglement shared across the network between the two nodes. And then the set of operations after that sharing of that entanglement, all of those operations are local, but some of them need to be controlled via the exchange of classical information. So these techniques were developed in the late 1990s and early 2000s. Sort of the canonical form here is that paper from Jens Eisert in 2000. With that approach, you can do quantum error correction in one of two ways. You can have your entire code word for the error correction inside one node, or you can have your code word for your entire error correction spanning across multiple nodes in your network. Now, obviously, putting them inside one node has advantages because it means that all of your error correction stuff just happens inside that one node, and you don't have to worry about what's going on in other nodes. Whereas in the other case, where you have distributed quantum error correction, where the error correction takes place between sets of nodes or across these nodes, then you need much faster rates of communication between the nodes in the system and much higher fidelity for them as well. And so the systems on the right are arguably orders of magnitude harder to build than the systems on the left. But the systems on the left require more capable individual nodes. And so there's sort of a trade-off there. Let's see, let me skip this part about how you actually go about building this stuff, just in the interest of time. So next question, and this is a good question where, again, the kind of systems engineer in this room can actually contribute, is how you deal with particular traffic patterns. So if we have a system that consists of a set of 4 nodes, and you've got a cloud in the middle representing your interconnect between those nodes that shares quantum information or shares quantum entanglement between them, the execution of your algorithm is going to involve a series of rounds of communication. And perhaps that first round is essentially in this loop structure here, and then maybe your second round is diagonally across it, and then your third round might be back to this loop ordered structure. So that's the traffic pattern in this, and it ultimately also drives questions about the structure of that cloud in the middle, and that cloud in the middle is really the focus of what we're doing. So for those of you who aren't familiar with this particular notation, quantum circuits or quantum algorithms are written in a graphical notation or represented in a graphical notation. They can also be written in lines of code. In this case, so each line of this represents one qubit that's actually being used as part of the calculation, and the vertical lines are individual gates between them. In this case, we've drawn lines, a red line and a blue line, that split this system up into 2 nodes, node A, node B, and node C. And the circled gates on this show 2 different approaches to achieving efficient communication between those 2 nodes. In the upper case, where you see sort of the dog leg in that, what's happening is that one qubit is getting teleported, meaning moved from one node to the other node, and then you do some operations with it locally on the other node, and then when you're done, you teleport it back. You send it back to the node where it came from. The ones circled in blue, in contrast, are the same as this remote gate that I showed you here, where in fact you're doing a computation between 2 qubits that reside in separate nodes, and you achieve that using the entanglement that's created by the network. This brings us to the network topology question, which is the real thing we're working on here. It's the new results in this. Obviously, those of you who are old enough to remember things like the Intel touchstone delta and things like that, large-scale parallel computers. One obvious idea is to take an individual node and then build it with connections going out northwest, east, northeast, south, and west into a larger system. And that would get you a system that looks something like this, which does remind me of the Intel touchstone delta. But there's one constraint here. This link between two nodes, the most common way to structure these is actually not, this is not a bidirectional link where you are sending quantum signals in both directions across this. What happens is that you send single photons from each node toward the middle of the link, and in the middle of the link, they actually interfere with each other. That requires that this system actually, in fact, looks something like this, where each of these extra devices in the system is actually something like this. Okay, so this, the cylinder on the left there is a cryostat running at 2 degrees Kelvin, which has single photon detectors in it, and we have to route all of the photons we're dealing with to that device. Which means that all of a sudden this nice elegant structure here starts to look really complicated when every single one of those gets replaced with a device like this. So instead what we want to do is put a set of computational nodes all together on the left and our detectors all together on the right, and we will run single photons through some sort of interconnect in the middle. And where those two photons come together at the detector, that's how we actually create the shared quantum entanglement between those two nodes at the top and bottom. And if we've done a good job with the structure of the network in the middle, we can have multiple connections crossing it in the middle as we go. So back to our supercomputer. This particular one has in it a dragonfly. And probably a number of people in the room are already familiar with classical dragonflies, where you have a group of switches represented by the sort of the peach-colored boxes connecting a set of nodes, which are the little pink circles, and then each group is connected to another set of systems there. So we want to sort of emulate this in a quantum world. What we'll do is we'll create a group structure where we have an optical switch in the middle and some set of computational nodes and possibly sensor nodes and things like that that all send photons to the switch. Some of those photons will go to nearby detectors, and some of those will get routed to other groups and other switches. And then, of course, the question is, can we build this? Right? Well, we're actually working on it in the lab. We have both simulation work and actual lab work. The lab looked like this in November of 2022. After a bunch of work by our students and our staff in 2024, it looks like this. And this is the structure of the system we are actually building, where the parts outlined in pink actually exist in the lab. So the system's actually up and running. Scale it up a little bit, it starts to look like this, where you might have some local communication between the nodes within the group, and some between groups, and some that actually goes via longer paths. And so the question is, how can we make all of this work together, building out something, as scaling it up as we go. And again, it looks like this, and this time with the labels of what those individual components on the systems are. This is the set of actual experimental results. On the left here, in sort of the center upper part of it, you see a thing that says F equals 0.94. That means that we have succeeded in creating pairs of photons that exhibit quantum entanglement, and the quality of them, or the fidelity of them, is about 94%. Over one hop, and over two hops, it's about 64%. That's in the middle, right smack in the middle of the diagram there. So that's not bad. So the questions as we scale the system up, what are the metrics we care about in doing all of this? Well, how far can we actually scale this up? How many detectors does it take? How many switches does it take? And ultimately, the evaluation of this, our mantra is, it's the decibels, stupid. We're going back to the SlimFly, for those of you who might be familiar with SlimFly. One serious constraint is the availability of good single photon detectors, and the question ultimately we care about is how long it really takes to execute application workloads like the quantum Fourier transform. And this paper is actually available on the archive, so you can get a preprint of this if you want. The links are in the slides, which are, of course, in Data Tracker. And I would say we have put at least a tentative checkbox on every single one of these things, but we still have lots of homework to do. And that's it. I'll take questions. Looks like we have about 4 minutes and 23 seconds for questions or discussion. Anyone in the queue yet?
Yeah, there's Dave in the queue.
Really simple question. How do you clock this?
That is a simple question with about a week-long answer. How much detail do you want on that?
You didn't talk about clocking at all. You sort of assume these photons all arrive at the appropriate moment in the middle, right?
You are correct, Dave. No, Dave's already sort of let's see. I didn't put in the detailed diagram for this. If you go and you look at the paper, there's a detailed diagram of the optical layout of all of this. And one of the items that's in the detailed optical layout is a thing called an optical delay line. And what it is it's literally a movable set of mirrors that adds a dog leg to the path for one of those photons. And you have to adjust the arrival time of one of those photons so that the two of them arrive together at the detector at the same time. That's true for the technology that we are working in. Slightly more extended version of the answer is it's true for our technology, but not necessarily for all technologies. The photons that we are working with are, I think, about 1.5 millimeters long. Some other technologies, in particular technology known as ion traps, they generate photons where the photons are hundreds of meters long. One photon is 100 meters, is several hundred meters long. Getting those to overlap is much easier than getting the shorter ones to overlap. And so they have a slightly different structure in their actual optical path. So it depends on the technology, but it's a great question. Yes, next question. Can you give us your name? Because I don't see you in the queue.
Sorry, Dejan Bogdanovic. The quantum error correction is very dependent on the quantum architecture. So not all quantum architectures, you can apply the quantum error correction. You require different mechanisms, as well as when you want to do the distributed quantum correction algorithm across QPUs, depending on which architecture you use, you will have to use different approaches. The interesting part is the network topology, because I believe that can be used across different architectures for the purpose of the entanglement.
Yes, that's correct. That's what we're trying to achieve.
The rest of it is specific to the quantum architecture that you are using in your lab.
Very true.
Yeah.
So you have correctly, you have more succinctly summarized our message than I have. Yes, thank you. I was trying to scroll all the way back here to that series of recent work. Here we go. So out of this work here recently, like I said, there's been a bunch in recent years. Almost none of it actually addresses the question of the network topology. And so, for example, one of the other very recent papers that's a tremendous paper, a super important paper, the ARC1 paper listed there at the bottom. I call that the Ang and the All-Stars paper. It's got like 30 authors and half of them are super famous people in the field. But it's very much about how you do the communication between two nodes without really addressing the question of what the network itself needs to be like. And that's the key contribution of what we're doing in this work. All right, we have 25 seconds if anybody wants to ask a 5 or 10 second question. Otherwise, I'll return the last 20 seconds or so to the chair. All right, thank you all.
Okay, thanks, Rod. Now it's time for speakers from below.
You want to introduce them, or do you want me to? So I collaborate with a number of people here in Thailand, and a couple of these guys are some of our local collaborators, and some of them are other local researchers that we don't yet have active collaborations with. So we wanted to get some local color into the QIRG meeting this time. So first speaker's Kyle.
Thanks, Ronnie.
Yeah.
All right. Fine. Cool.
You have a timer there that's including Q&A.
Oh yeah, half an hour, right? Okay. I try to use this one first. Okay, fine, good. Hi everyone. First of all, just wanted to welcome you guys to Bangkok and Thailand as well.
Stand just a little closer.
So closer. Okay. I think it should be better now. Actually, I have to fly from. I'm South Thailand, so I have to fly from city called Hat Yai in Thailand. And my first time around this region of Bangkok anyway. Well, I am assistant professor Prit Krasuwan from Pranav Songkhla University. I come with my colleague actually, Associate Professor Suchin Suwanna and Dr. Pong Chang. They just sit over there. They may come to give a talk and share their expertise later in this talk. So yeah, I try to talk. Try. It's good. My great opportunity to come here to give you the update of what we have done in Thailand so far. Yeah, most of the works, all the works, not my work, is just from my colleagues that we collaborate in so many universities in this country, and also Professor Rodney and Kale University as well with Associate Suchin. So we have me, Prit Krasuwan, Professor Ajahn Suchin Suwanna and Pong Chang from the company called QIRG China. Let's talk about the history first. Our journey started from 4 years ago, when our government just realized that quantum technology may be something, maybe some some important thing in the future. So they launched something called a white paper in ago, and the aim of the white paper that the 10 years after they launched the white paper, they hope we can have the quantum internet in 10-year time and some quantum sensor for commercialization and quantum computer that they want to that what they expect for it. And it's great that for the map, I think we are the first country, except Singapore, in the region that can, color this map. It's one of the red one. In this 4 year, I can say that the funding is not much. It's not just 6 million USD, but it's good to start with. It's also useful for us to start with everything. We collaborate with some colleagues in ASEAN as well. We have Philippines on the map already. I think Malaysia, Indonesia will be soon, as far as concerned. So we try to translate the text of the roadmap into the picture and the action. Because my headquarters my affiliation in the South. So we plan. Very first year we try to do things in the lab. We try to do quantum communication. We try to do the quantum network. Try to do the QKD in the lab first, and we expand to the country, to the whole country using the quantum internet. At the end, yes, it's just the dream. Hopefully, we can make it done as we expect, as we promised to the government, like the picture. And not just only talk domestically in Thai only. We would like to connect to the world through like satellite thing, to quantum network using the satellite, using the ground station kind of in the future as well. So we need collaboration, and this meeting will be a great opportunity to find the collaboration worldwide with all of you guys in this meeting.
Sorry, Pruitt. So back, yeah.
Yeah.
Normally, we don't interrupt people while they're speaking, but I can't resist. So these dates that are on this, that's not 500 years from now.
Yes,
that's some
no
local
number. Buddhism. So if you have Christian year, right, you have to plus 534 to that. Yeah, 543. Yeah, 543 to that. So you should subtract number here using 543. You will get the year, the precise year of the Christian, the norm,
So what year is it now? Is it 2569 now?
68.
So it's 2568 now.
I
Okay,
forget
so
the
this roadmap you've got here starts next year.
Yes, next
Okay.
year. So we see, I'll come to update again next year then. Oh yeah, I forget to change the year actually. Yeah, so 2571 as well. So to start a quantum network, hopefully. And I would like to, this slide she's just overview that. So we have 3 speakers. So I divide the program into 3-4 things, depending on the component we're working on it, and also the PQC also. So we talk about the thing I highlight the red thing. So Sujin will come to talk the blue thing, and Pum Pong maybe come to talk about the green thing in this slide. So otherwise, in our mission in the component like that. So from the picture you can see that we work in every area. But I would say that many things we do reward engineering. We do try to catch up the technology. We try to implement them. If we have some opportunity to improve it, we do it. And there's example of the thing that the excellent achievement for the 4 years, like 3 years ago, we can do the fundamental thing, the most fundamental thing of the quantum communication, just to build the source, just to build a quantum entanglement source. We can reproduce the work of Nobel Prize to 2022 nicely. We can do this thing in many places in Thailand, in the south of Thailand, in my colleague in Thammasat University in Bangkok, and I think it's also Sujin in Mahidol as well, in Bangkok as well. We can do the source, the same thing, the fundamental part, the most important thing, the most important part of quantum communication. And not just only get the entanglement source, we can also have the ability to capture the picture of entanglement photon. You see the 2 pictures, the 2 circles, the same picture, different year, but actually they have a different efficiency of how can we take a picture of photon. We're not going to use the photon imaging for just communication. We're looking forward to using quantum sensing for the medical application, for example. And for the free space BB84 demonstration, we can do it as well. We can at the moment we work on this thing for 2 years already. We can do the first demonstration for like 100 meter QKD BB84. But the thing is, the positive thing about it is that it's better every year. We can go longer and longer this year, and we think we have the new technique to improve the quality of the signal that we can transmit to the free space as well. And our circuit we can use some technique also to make it very robust when we try to use it in practical environment also. Not just only for the free space, we're also thinking about the post-process and pre-process of photon using the chip, the photonic chip. Because my background is that 10 years ago, I got my degree from Bristol University. They're working a lot with photonic chip. But I work on mostly in bulk optic back then. But when I come back to Thailand, it's my first time to catch up with the technology of photonic chip. Unfortunately, many of my colleagues there in Bristol have already have the company that can provide a very good chip for me. So we're using silicon nitride to do some simple thing like quantum random generator. For the first time, for the first experience for that, we got very bad random number generator. We don't quite have 0. We have 0 and 1 for sure, but not very balanced. It tends to be 0 but then 1. It's a lot. Like you can see in the picture on the right side of my hand. And we use some technique as well, and some de-biasing process, post-processing physically as well. In the optic, we can make this random number to be better, to 0 and 1 to be more balanced, for example. I think that's all from me. Professor Sujin will come to talk about his work. So,
We'll do all 3 speakers together, and then we'll take Q&A
Okay,
from the
all
3
right.
together, I think.
Thank you so much. I would ask Plit to give the talk of my work, but that would be sort of awkward since I'm sitting here. So, I am a physicist, and the part of the contribution that I do for quantum communication would be looking for physical systems that could be used as elements in the network. And at the moment, I focus on single photon emitters and quantum memories. And the other part for my contribution would be some sort of optimization or entanglement distribution strategy on a network. So the first part of my talk is collaborated with a group of research in Technical University of Munich in Germany. And the second part is collaborated with Rodney Sensei sitting over here. And the summary on the table here is some emitter systems that is for now kind of famous as being looked at a lot because it's actually hosted by a wide bandgap material, hexagonal boron nitride. And that means it can persist thermal fluctuation, so it can be operated at room temperature. And there are a variety of hosts like this, and I summarize this on the table and highlight two in particular. So my work then would be basically computing on the photophysical system and look for appropriate wavelength for application. And one for QKD, for example, would be the Van Hofer because it can be used for daylight QKD. It has minimum absorption from the atmospheric, for example. The other one is the system that would be compatible with and NV Center is good for sensing. It's also good for quantum memory, for example. There are other systems in this environment that also good for quantum memory as well. And that would be for the next slide. And this one, also a bunch of physical system, again, hosted by hexagonal boron nitride. And we sort of construct a model to evaluate whether this system is good for being a quantum memory or not. And there are key parameters, for example, the coherence time, the coupling, and how much of the, what we call the quality factor in the cavity that is required for that system. So we can use this model and we can kind of identify the defects in HBN so that our colleagues can do experiment and verify that experimentally. So this is that work. And the outcome of this is that we created a bunch of, it's basically a database of a physical system that is good for quantum emitters and good for quantum memories. So you can visit that website here. This is hosted at the CIT in Munich. The other part of my work is to run quantum network simulation to optimize certain strategy. And that includes the first generation, second generation, and the third generation quantum repeaters. And there we are trying to analyze what strategy is better. The outcome of this is that the hybrid strategy that includes purification encoding is better than just entanglement distribution, just entanglement swapping. Entanglement here is being used as a resource at the node, and therefore it has been presumed to be created and stored in the node already. And before you send it, you can just basically send it at the 0G, just send, then perform entanglement swapping, or you can just, then you can use multiple entanglements and purify entanglement first before you send, or send first and then purify later. So various strategy. You can look at in the QCNC paper, I guess, and this is the graph of that report. You can see that some hybrid entanglement is actually, some hybrid strategy is better than just the pure strategy. And to have something that we tell you is a toy model, use what we have created to question whether we can perform 3-node network in Thailand and still meet the QKD requirement, for example, using range of errors. And it turns out that if we assume, like, for example, 0.5 dB per kilometer of photon loss noise and about 1%, sorry, maybe even 0.05% of measurement errors, then it fails in Thailand. Sorry. So that's the contribution. And then the other part, Dr. Pumpong will talk about.
Hi, my name is Chemongkot from Quantum Technology Foundation, Thailand. So I was assigned by seniors over there to talk about more ground level and more. Raise the microphone. Okay. Better now? Oh, good. Let's start over. Take two. Hi, my name is Phumpong Chevongkot from QTFT. I was assigned by my senior over there to talk about more ground level and more implementation level of quantum key distribution and quantum network in Thailand. So basically, it's not avoidable that one day we will have commercial system in Thailand or in anywhere on earth that gonna deploy in our country. So in the bigger picture, we need to have facilities and have a method to characterize and verify the system that, okay, if someone claims that they have entanglement photon, single photon source, single photon detector, it actually does as they claim. So this is our collaboration with NIMT, National Institute for Metrology of Thailand, on create a facility to test single photon source and single photon detector. So if this goes according to plan, we're gonna have this service by next year or two. Yes. And the other part is if we gonna have a system, a QKD system, that the security is really based on physics system. So we have to have a way to really characterize that it works as intended. And also if any unintended feature or bug, we need to catch it in physical level. So right now at Prince of Songkla University, where Dr. Prut, the first speaker, is, we are trying to reproduce any known attack on quantum system and try to characterize and try to implement the suggest countermeasure or find our own countermeasure for any attack. And hopefully we're gonna have that record to have like when we have a standard for Thai QKD system, we can add this into our testing system the same way as other countries have. On the regulation side, we also know that, okay, every other country, many other countries has their own standards or their own recommendation about QKD system and post-quantum cryptography system. Also, like both in the device itself, on the network, or on the possible attack or countermeasures. So in Thailand, we also work with NCSA, which is a National Cybersecurity Agency. Right now, their focus is on post-quantum cryptography implementation, which is basically a big patch on the program in the network, right? So to update the encryption system on the software level itself to handle quantum threat. At least that's the quick measure for now until we have QKD network ready. So at the end of last year, we have a guideline for post-quantum cryptography migration for local Thai agencies or companies to follow. And the more detailed guideline and regulation updates will come out later this year. So yes, that's all update on what you call local research site. So yeah, we try to have quantum network ready, or at least quantum resistant network ready before quantum technology become problem. So thank you.
All right, thank you. Questions, comments, advice? While we're waiting for others to get in the queue, I actually have one about your last slide, or one or two slides ago. Yeah, this. Yes. So NCSA is who?
It's National Cybersecurity Agency. It's one of the agency as part of the Ministry of Digital Communication, if I remember the name correct in English. So they are the regulator for any secure communication in Thailand.
So it's an actual government agency?
It's national government agency, yes.
Other questions, either in the room or online? We have Soeda-san, Akihito in the queue.
Hi, thanks for the talks. Maybe I missed it, but
Hey.
I understand you're right now working on QKD, but what about quantum repeaters? Can you comment on that?
Quantum repeater?
Yes.
You
I
mean
know
comment on?
First generation, second generation, third generation slide.
Can you speak just a little louder? It's a little, your voice isn't real strong up here.
Better? Okay.
Yes.
Yeah, so I think there was one slide at least on showing first generation, second generation, third generation repeaters. But do you have any experimental work on that part as well? Wait, you need to go to mic.
Come.
Or that mic would be fine.
Okay. Right. Thank you so much for the question. So the quantum memory works is done separately. In fact, we have not done experiment in the lab for that. The 1G, 2G, and the hybrid strategy, that is a simulation work. And in there, we did not include quantum memories in it.
But you have a lot of database that on the material properties of quantum possible quantum memory devices.
Yeah, so you can think of this as two separate research that are more or less in a big picture would be part of quantum network or quantum communication. So the part on physical systems, including quantum emitters and quantum memories, those are computational, theoretical, and at experiment, but they have not been implemented in the actual network.
Okay,
Yeah.
I guess many of the audiences here are not from physics background, so maybe you can comment on whether, so do you think whatever you're trying to develop would have a easy interface for people not from possibly a physics background to use it? Do you think you'll be able to, are you thinking about that kind of user interface for your simulation? Or maybe for that database? So how much background knowledge do you need to exploit to utilize your database, for example?
I am not quite sure. So you would like to know the interface?
No, just so if you want to use this database, right? For example, how much do you need to know like physics to be able to use it?
How much physics?
Yes.
To be able to use it. I'm not sure if I understand.
Well, take a I don't know a standard standard level computer science graduate student, right? Do you think she would might be able to use it, for example?
So, for example, if okay, so the actual implementation and the actual certain properties of it that we need. For example, if I can tell you that for now, the coherence time for NV center, for example, if it's stored in the electronic spin state, then it would be at the microsecond level. On the other hand, if you map it to the nuclear spin state, then the coherence time, which is good for storage, could be improved by 3 orders of magnitude. So it would be in the order of micros or millisecond, for example. And so if you know that, then you kind of know how much time you operate, and that can compensate for the delay of the 2 photons that would arrive at different repeater to perform, for example, entanglement swapping. So such parameters could be used in the optimization of your quantum network. But at the moment, we perform experiment to really verify how much, for example, memory times or how much errors is going to occur during such delay. So information like that will probably be useful for optimization of your network.
Sure. So I mean, there's a lot of work trying to develop sophisticated network simulator for quantum repeater networks. But maybe you might try to sort of combine your database and the simulator so in near future. That's the
Right.
thought.
So one part of the work is basically to characterize all of this. And then what we have not decided on what would be the perfect or the ideal quantum memory for certain task. It also depends on the incoming photon. The coupling would also be important. But at the moment, the physical property of a quantum system to be used as a memory is not known. It's not well known. I mean, we can kind of guess what would be the coherence time for certain specific systems, and that depends on the environment too, not just itself. In the model that I show you, it really depends on the, for example, the detuning gap, the intercrossing between the storage state and the excited state, and the incoming photon. And that doesn't include the interaction between the physical system with the thermal bath, I would say thermal bath, that would be surrounding that particular physical system. So we are trying to understand that. And if you can have a system that is in a wide bandgap material, like I showed you before, then part of it would be good because it already isolated from thermal fluctuation from its environment. So that's good. But then you have to really make sure that the quantum state that you are going to use for quantum storage would have to be near the center of the band rather than at the edges of the band. Because if you're at the edges of the band, then either photon absorption or photon emission would kind of destroy it.
So we've gotten kind of into the very detailed stuff here. So maybe the two of you can take this offline over lunch. I invite you both to join us for lunch.
Okay, thank you. Sorry.
Other questions?
Yeah.
Yeah.
So while we are waiting, if you're able to add on the comments just now, is that on the user interface and how hard it is to use for what kind of experience user gonna have. So right now we are working on scientific part itself. So it's like implement the hard parts, but in the end, when we're gonna deploy it or use it, it should be easier to use or easier to understand. Yeah, the same way that we don't know how Ethernet really works most of the time, but we still use it right now. Yeah.
All right. So I don't see you in the queue.
Yes.
Can you give us your name?
It's Michael. Okay. It's mentioned that you have some practice on the QKD and the satellite technologies. And the QKD it's said that it have a short distance with 100 meters. But you have the plan to have it more longer, like the kilometers?
Yes.
40. And another question is about the satellite. What kind of satellite you are trying or planning to try? Is LEO, MEO, or GEO for delivery the quantum keys?
You mean the satellite?
Yeah.
Okay.
Yeah.
Okay. So our plan right now is that limitation for say fiber-based QKD itself. If you're going to use single photon through fiber, it's like 100 kilometer or at most 200 kilometer, depends on protocol. Okay. So say for the local area, like in one city itself, we might rely on we may rely on the fiber-based network that can reach 100 kilometers. But right now, when we said we implement 70 meters demonstration, it's not the limitation of our device, it's limitation of regulation. We cannot shine laser outside easily in Thailand. So we have that hallway that's 70 meters. Actually, that's the regulation limit. But by limitation of the device itself, we can reach several kilometers. Actually, for our plan, as Dr. Prut said earlier, that we plan to have a ground station for satellite communication. So yeah, we are looking for collaboration on that part as well. If anyone has satellite that want to talk to us, so yeah, that's we can cover thousands of kilometers easily with that setup.
Okay, thank you. Thank you.
Thanks.
All right. Nobody else in the queue, and timing's pretty good. So thank the three of you for that update on what's going on here in Thailand.
Thank you.
Is there one more? There one. I don't see.
Thank you.
Yeah. Okay. Thanks to the three of you. All right. Wojtek, who's up next?
Oscar is next. Oscar, can you switch yourself on? And I believe you want to share your screen. So you'll have to request your screen share.
Hello, I'm Oscar van Deventer, and I'm requesting the screen share, and hopefully you can see my screen about now. Yeah. If I click share, click. Okay, this is highly annoying. It says I want to share, and when I click hard on my computer, everything freezes. Okay. Let me have another attempt. I click again on request screen share. It says permission denied. Do you want to share the screen? Yes, I want to share my screen. Click, share. Sorry, this is one of those things that I could not do. There we are. Sorry for that. Hello, my name is Oscar van Deventer. Hopefully,
just 1 second, Oscar. I'm going to switch on the timer. You're going to have 20 minutes. That includes your Q&A. Now you're free to go.
Thank you, Wojtek, for introducing me. Hello, I'm Oscar van Deventer from the Netherlands. I work at TNO, which is a Dutch research institute, and I have a telecommunication background. And at this moment, I'm deeply involved in European standardization for quantum technologies. So my presentation today is about the modeling of quantum repeater chains. And I would like to invite you to go to the meeting documents and to look up my document. And it also provides my email address because it has actually a call to action, which I'm going at right now. So my contribution, it models nodes in chains of quantum repeaters at two abstraction levels. First of all, the nature of the interfaces, but also the functionality of the nodes. And the purpose of this classification is to have terminology to classify equipment for design, planning, and configuration. And my call to action to all of you is please provide me feedback at my email address or maybe even at the meeting. Is the proposed modeling, is it useful? Is the timing right for this modeling? Is the Quantum Internet Research Group the right place to do this? And how can we best document this? So let me go to the details. And let me first show you figure 1. So we are talking about pre-standardization, and what is the reason why we have a standardization that's about supply chains? Because people want to buy and sell things to each other. And so let's start with the supply chain for quantum repeater solutions. So QR means here quantum repeaters. On the far right, you see the customer which is using the quantum network, the quantum network operator, going to the left, the systems integrator, and then you have vendors of components, which may be pieces of software, hardware, or other types of components. And at this moment, the scope of this document is all the way on the left-hand side. So whereas quantum repeater chains themselves in the market probably will be sold as a whole. So you buy a quantum repeater chain from a single vendor, but the integrator will need to combine multiple pieces of software and hardware to build a quantum repeater chain. So that's why we focus on that aspect. So let me go to the next picture. So this is the a telecommunication style model of a quantum repeater chain. It is very abstract on purpose. You have the customer domain, which has user equipment, which may be Rodney's quantum computer. You have the quantum service provider domain. So QSP is the quantum service provider, and the quantum service provider provides, operates a quantum repeater chain and connects it to another customer domain. And at the customer premises, you have user equipment, UE, an end node, which is a QSP node, but it's at the location of the customer premises. Then you have the QSP premises, so the nodes of the quantum service provider. And you have so-called user-to-network interfaces and network-to-network interfaces. And obviously, this is at a very abstract level, but the whole, as I already explained, the whole purpose of introducing this is to provide terminology to talk about these things when you're purchasing parts for this chain. Going to my next picture, and of course, I highly recommend all of you to read the document. You can download it, as I mentioned, at the IETF data tracker site. So what we note is that we have actually in the quantum domain two types of ports: the transmitting port and the receiving port for transmitting and receiving photonic qubits. And this means that you have a total of 5 types of network elements. You have end nodes, which have at the network-to-network interface a receiver or a transmitter, and quantum repeaters you can also have in 3 flavors: receiving. For instance, a Bell state measurement is a type of receiving. It can be transmitting. For instance, an entangled photon pair source is transmitting. And you can also have the combination of repeating, transmitting. And the purpose of having this classification is that you can start modeling timelines. So when you we know already about the multiple generations, and in the first 2 generations of quantum repeaters, you will have entanglement swapping. So you can check the timing of the photonic qubits and the classical communication to see, calculate at what time you have achieved entangled photon pairs, or at least the entangled qubits at the end nodes. Going even further down, this is the 4th figure, looking even a bit more at the functionality that you can have inside of a quantum repeater or an end node. So we all know these functionalities: entangled photon pair source, Bell state measurement, quantum memory, time tagger, local operations. You know, the electronically controlled X or Z operation to, for instance, for quantum teleportation, and of course functionality for classic communications. And again, this is modeled at a very abstract level by a telecommunication engineer who is not a quantum technologies expert. So this picture shows you some examples of configurations for modeling the quantum repeaters. And again, I need to highlight that these are abstract models. It does not reflect exactly what is inside of a quantum repeater. So a quantum repeater may be an NV center, which combines a matter qubit with a photon qubit. And you may model this in abstract terms with maybe multiple of those components, including quantum memory, entangled photon pair source, Bell state measurement, etc. And what you see in all of these examples, well, example A and B are the classic or the well-known single components. But if you combine more of them, for instance, you can introduce the function of heralding. and more functions. And at the bottom right, you see an access node or an end node of the T type, where you have a local entanglement entangled photon pair source and the quantum memory, but then combined with local operations. So, for instance, if you get the input that, okay, for your entanglement swapping, you need to perform an electronically controlled Z or X operation, then the classic communication, that's CC, can achieve that. So here I have shown you several pictures of my presentation. Based on this modeling, we can categorize 4 categories of classic communication, CC functions. You need synchronization, which needs to be very time accurate, but is not necessarily latency critical. You have a quantum repeater protocol, which is, for instance, for signaling Bell state measurement results and photon loss. It's latency critical, but not necessarily time accurate. You need to have proper administration for this. The FCAPS protocol, this is telecommunications for terms for management. So it's functionality, well, I keep forgetting performance, accounting management, configuration management, etc. And all the management is, of course, not latency critical, nor does it need to be time accurate. And finally, the local decisions, the controlled, electronically controlled X or Z operations, they are really need to be time accurate, and it's also latency critical. So these are 4 protocols. And for each of those 4 protocols, I can imagine that there will be a market for software stacks for those, and you want to make them interoperable. So all of my presentation would be input to the development of such protocols. And I have come to the end of my presentation. So the question that I would like to ask to the community, and I will go to my questions again. Thank you. That is, please provide me feedback. Is this useful? Is this the right time? Is this the right place? And more. Thank you.
Thank you, Oscar. If anybody has a question, please raise your digital hand and enter the queue.
While we're waiting for others, Oscar, I have a question, which is, so you have a draft of a document here that's already started. What do you want to see happen with this document? What do you view as the potential outcome of this work?
That is a good question. And actually, this is exactly the thing that I'm struggling with. So this is why I'm asking for feedback. So I could imagine that this document is somehow transformed into a QIRG document, and it would be like an extension to the architecture document that has already been made by or published by QIRG about a year ago. So that is at least one of the options.
There's definitely was interest in taxonomy at some point. So I can actually, seeing the talks that have been here so far today at this meeting, there is a gap between the physicists and the people working above on top of the physics. And what I find very useful from your contribution is that you're trying to provide this effectively human interface about how to talk between the different groups of people, so that the groups of physicists can say, this is the component of your picture that I am referring to. And then the people above who want to then talk at the network level can then refer, well, assuming this functionality, this is how I think this will work. Whether it's the right time, I think it's hard to say, but maybe it's worth a shot. Given that there's no queue of questions, it may be something worth pursuing in smaller steps on the mailing list. It may be that the document you have sent is just a lot to take in one go. But actually there is a question also, I'll let Diego talk in a moment, but it's perhaps a lot to take in, but I definitely do see space for it on the mailing list but I would focus on trying to get an understanding from the participants in the mailing list, what would be useful for them. I think that would be the most important part of this interaction. And with that, I'll pass. I don't know if you have any comment on that before I pass to Diego, Oscar.
Thank you for that advice. I already posted this contribution on the mailing list a week ago. So far, it has not provoked any responses. So, Wojtek, Rodney, I will be in contact with you about doing this, getting more detailed advice from you how to approach this best. And yes, I'm aware that this is a lot to take in at once. It's a big rock in the pond.
Okay, Diego Lopez here. Just when you mentioned, Oscar, about putting it on the mailing list a week ago, a week before the meeting is something that normally makes many of us not be very reactive. That's to start with. Apart from that, I see a value here because what we're trying to do is to imagine how the quantum internet will be in the future we don't have something that looks like a real quantum internet yet at hand to play with seriously, at least. And the idea of modeling the different elements and analyzing which are the implications for not the hop-by-hop links, but the real quantum links end-to-end, etc., and analyzing which are the characteristics, etc., and at least deriving some requirements for the for protocols and the desired characteristics of the quantum repeaters. Now that they are starting to be announced and there are some pieces to play with, I see a value here in analyzing what would be the potential protocols and principles that we can apply in building the different kind of links that we have to consider in the future. So this is a research group, why not? So I would say, yes, go for it.
Thank you.
We have our incoming IRTF chair in the room. Dirk just had snapped up when I said that. I'm going to put him on the spot here in just a minute for maybe a suggestion or two. But before I do that, just as a comment, it seems like sort of the home run endpoint of what you're trying to do here would be an informational RFC as an outcome of this. And which means, of course, that in general operations terms, it likely will be a collaborative document rather than just a single author. And so just procedurally, we would want to put it into a shared format or some tool that allows for collaborative work on the document in some way, shape, or form. And just FYI, as was discussed yesterday in a different session, of course, the process of going from first version draft to a published RFC often takes years. Our first RFC out of this research group, RFC 9340, I believe, took us about 4 years. And so of course, that depends on how hard people work and how hard or how much they focus and how hard they push. But it takes time to sort of build shared consensus on these things. And as a personal opinion, I think doing work on taxonomy and defining the concepts actually is super valuable work. And we've done some work in our research group, my research group, not here at QIRG, on defining the node types and what they should mean and what they're doing. And our goal in that work actually is to deliver documents that define the node types and interfaces and things like that. And I'll be honest, we are what I think of as way behind in terms of actually producing the deliverables on that. So I would be happy to personally to either contribute myself or get people from my research group to contribute to this if we go forward with this. For example, one example is that the node known as a switch. Some people use the term switch to mean a repeater that has multiple interfaces and that operates like a full repeater. In my research group, we reserve the term switch for a thing that routes photons from place to place without memory and without the full functionality of repeater. So that's a difference in the terminology, which I suspect is resulting in some misunderstandings among people who are reading things, and resolving those and having one good source and one shared vocabulary, I think would be a huge win. And Dirk has indeed come to the microphone, so he might have some suggestions on where we can go and what we can do with this.
Yeah, hello, I'm Dirk Kutscher. So in principle, there's of course no issue in like going for a document that will become an informational RFC in the future. So I think Oscar and the chairs probably need to think about, so what is the purpose of this document? So is that something that is useful for like a broader audience, so outside of this group? Then, and if it's like a quality document, then it's, I think, worthwhile publishing in an RFC. If it's more like a document that helps, informing the discussion in the group, you have different options. You could write it up in an internet draft, and then it's kept updating over time. It's great. But we also have experience with like just having a living online document. So it really depends on what you think is the purpose of this document, and also how often you think it needs to be updated and so on. But we can use all the tools, and we also don't necessarily need a broader consensus. If you still think it's useful and Oscar goes ahead with it, it's also possible.
Thanks, and we are over time here at this point, so we need to cut this off here and go to our next couple of presentations. Thanks, Oscar. So I think next up actually is Wojtek himself. Wojtek himself has set himself at 18 minutes here. All right, go.
Hi, everybody. So today I want to talk about what's the title of the slide, which is Quantum Advantage without Quantum Memories. And I hope, having seen some earlier talks today, we can see that there's a lot of progress on quantum memories, but it's a difficult technology, and that will help me motivate what I want to present. Oh. Yeah. So why even talk about quantum advantage without quantum memories? First, let me define these terms. Quantum advantage you might often hear in the context of quantum computing. Here I talk in the context of quantum communication, is the idea that with a quantum network we can solve some real-world problem in some better way. Faster, more securely, more efficiently, more effectively, more something. In some way it creates value for somebody. Unlike in quantum computing, we can talk about things more than just power, computing speed, etc. Security is in itself an advantage. Quantum memory is just storage for quantum states, entangled or otherwise. And here I want to talk about how can we get a quantum advantage without actually any quantum memories in a quantum network. Again, why talk about it? So in 2018, a few professors from TU Delft published a kind of roadmap for the quantum internet, which defines 6 stages of the development of the complexity of the quantum internet. Today, we're at the first stage. It's called the trusted repeater stage. I put there EuroQCI. Europe has this massive initiative called EuroQCI to deploy a massive trusted repeater network across all of Europe. Trusted repeater here stage means we're doing only QKD, and all relaying between nodes is done via trusted repeater nodes, which means you actually break the quantum connection. You translate the signal to a classical representation, and then you relay it further. In a sense, it's not an end-to-end quantum connection. You do quantum links one by one, and you're able to glue the key in this way. And then there's a lot of ambitious initiatives going beyond that. For example, again, all my examples are about Europe because I'm from Europe, so I know them best. There's more work outside, and I hope you have seen that there's quite good work all around the globe today. The Quantum Internet Alliance, which is a European collaboration, is aiming for the quantum memory stage. It's the fourth stage, the idea that you have a quantum memory where you can store some quantum states whilst you do some communication whilst you're storing that quantum state. They're aiming for a prototype by 2029. Prototype and 2029. Well, that's all far away. Well, for me at least. Obviously not in the grand scheme of things, but these are years now. And the question I have is when I look at this roadmap is like there's two stages in between and there's not much, at least I feel there's not much attention given to those stages. And I feel it's a bit of a shame because the devices we use for trusted repeater networks can be used actually for what's called the second stage, prepare and measure, with the caveat that you cannot then repeat the signal, which means you are bound by the 100 to 200 kilometer distance limitation. And as I'll show in 2 slides later, I think that there's already vendors on the market selling entanglement sources, which in principle means we're getting to the stage of entanglement generation networks just without quantum memories. So just to give you a scope of the Euro QCI, it does literally cover almost all of the EU, and this has been in progress for the last 2 years. There's currently an ongoing call for now connecting them across borders. This is going to keep going. This is not a finite small project. Europe is heavily investing into this. And the thing is, the focus is QKD, because you can do QKD, you have vendors who do QKD. But we can use the same hardware to go beyond that. And this is kind of where I come from, is because we're going to have this massive infrastructure. It's a bit of a shame if we couldn't at least try and do something more with it than just QKD. And yeah, as I said, there's vendors selling entangled photon sources, which are meant to be compatible with telco infrastructure. I know the pictures they use, at least maybe the top one shows you that this is something you can install in a rack already and can run in a network. The bottom one doesn't really look it, but as far as I understand they also do have a rack mountable product. These are from 2 companies that are online. The top one is from QNEC, the bottom one is from Quantum Industries. Top one is American, bottom one is from Austria. So these things exist, and so therefore in principle we could start buying this and start building more complex applications beyond QKD. So how do I want to approach this problem? It is problematic. People don't work in it because it's a bit difficult to actually come up with what's a valuable application. QKD is kind of the obvious candidate. And then in quantum memory stage, there's some other candidates because now you can start connecting quantum computing nodes. But what's in between? So there are inventories of what you can do with quantum networks. There's, for example, the Quantum Protocol Zoo, the link is there. And in November last year, a very interesting review came out, which is about all the various cryptographic primitives beyond key distribution. And there's also an RFC actually from this group on application scenarios for the quantum internet in terms of inventories. The problem I find with those inventories is that they often dive deep into the mathematics, the technical details, not the RFC, but the other 2. They dive deep into the technical and mathematical and theoretical background, which again is very important, but it makes it very difficult to figure out what you can actually do with those applications. And they also often include applications from all stages of quantum network development. They tend to not do a cutoff between the stages of development, which is a bit distracting because all the most valuable ones are indeed in the quantum memory stages and beyond. So what I wanted to do, and I want to present here, maybe I should have shared it on the mailing list before, but at least here I will present the concept and maybe get some initial ideas and trigger some discussion. So is create an inventory that focuses on functionality over mathematical detail and is limited to memory-less stages, so ones that can be realized today or very near term. Why do I think this is relevant to QIRG? Well, first, I'm sure I have this question, and I'm sure a lot of people in this room have a question. What are quantum networks for? Like, what can we do them for? So having an inventory of applications that can be done today rather than across the whole spectrum of time could be useful. Understanding the use cases will help us understand how to build these networks. They're not all built the same. They have actually quite significantly different requirements depending on the use case. And also, the last point is something I do strongly believe that will be the case. Quantum entanglement networks will not come out of a vacuum. they will evolve from the currently being deployed QKD networks. And so therefore we need to have a concept of how these networks will evolve forward. It's not like there'll be QKD networks and one day we'll start deploying entanglement networks in parallel. They're all quantum networks. So with that motivation set out, I kind of want to go where I see possible. I've done a bit of a scan of the literature, and I want to kind of present where I see potential advantage before we have quantum memories. And I want this to trigger a bit of discussion here or after, and see, or the mailing list. We'll see. I basically found 4 domains where there's advantages over security. There's more to QKD than I'm just going to say. Position verification, unforgeable tokens, and tacit coordination. I'm going to go through them one by one now very briefly to explain what they all are. So security, first of all, there's more than just quantum key distribution. There you have applications, many other security primitives can still be done with quantum networks, such as fingerprinting, digital signatures, bit commitment, oblivious transfer, strong coin flipping, weak coin flipping, and one-time programs. Some of these things are building blocks for secure multi-party computation, such as bit commitment and oblivious transfer. Some are primitives for consensus protocols, such as the coin flipping applications. The thing is, in general, all of these things can be done classically. That is true. And that must be always taken into account in the sense like, why invest in a quantum network if I can already do this? So quantum provides in general an increase in security. Sometimes it can take something up to information theoretic security. Sometimes, not always. Sometimes it's only just weaker assumptions. But generally, they're also secure against quantum computing attacks. It's quantum, so generally the first question is this secure against quantum computer? Sometimes, but actually very often, the security comes with some deployment or implementation drawbacks, so there's always a trade-off here. It's really not obvious always when to use a quantum primitive over just a classical implementation. And for context, information theoretic security, possibly under some special conditions, so not generally, not in all cases, is possible for quantum key distribution, digital signatures, bit commitment, and one-time programs. The other ones do not have that benefit. They're going to be under some computational assumptions. Sometimes this computational assumption is simply you cannot have yet a quantum computer with 1 million logical qubits, and as we go forward, maybe it's not 1 million qubits, but even more. So they're computational assumptions of a quantum computer, not classical computing. And the key question for these security applications very often is, where is this increased level of security needed? For most cases, and as we can see, there's a lot of work in the IETF on post-quantum cryptography, and for most cases, it's much easier and sufficiently secure. But there are some high security domains that do rely on additional security measures, so therefore this is where it could be useful. And my question actually is, can information security enabled by quantum allow us to automate tasks that are currently delegated to people in government, military, finance? And actually, I work for SURF, which is a research and education network provider in the Netherlands, and actually a common problem that SURF faces is the compute resource is very often in a different location than a data source. And if that data source is under some regulation about restricted to a particular location, then things become difficult. And you need to start thinking about serious security measures. And my hope is that maybe with quantum, we can allow for new things like secure compute data environments. Anyway, so question ultimately is, can ITS enable, by quantum help secure virtual environments for compute and research, for example? So that's on security. Another thing is position verification. Position verification, what is it? It verifies that a given message originates from a particular geographical location. This is interesting. I'm told this is not possible classically because all classical methods are vulnerable to collusion attacks. So this is a genuine quantum advantage where you can generally do something that is not possible to do without quantum. It's not information theoretic secure though. It assumes a bound on the adversary. It's limited, your verification is limited to where you have the quantum nodes, so not exactly, you cannot just verify somebody on the mobile phone. Intuitively, it could be useful in military and other high security domains. Can it be useful in other domains? It's actually a bit of a shame that a certain buffer network attestation was in parallel because maybe it could be useful there. I don't know. Maybe it's useful for verifying locations of a DNS or BGP node. I don't know. If you think ability to verify these things cryptographically is useful, that'd be really cool. Other than that, authentication, you can now add location to your two-factor authentication for some applications. Maybe gaming. Maybe now that you have a cryptographically secure way of verifying the location, maybe you can enable new possibilities in gaming because you don't have to employ various other methods for detecting cheaters. Maybe. Unforgeable tokens. Unforgeable token is basically money, but phrased as a token. The idea is a central authority releases some tokens that cannot be forged. Most common schemes such as quantum money require quantum memories, but it actually is possible to implement unforgeable tokens without quantum memories if you can verify things at a network of trusted agents. There is a quantum advantage, but it is a bit smaller than in the other examples. Classically, there's 3 properties one might want out of tokens: unforgeability, instant validation, and user privacy. Classically, you can have 2 out of 3. With quantum mechanics, you can have all 3. So you can have unforgeability, validation, user privacy. Where would all 3 be useful? I don't really know. The academic papers from which I got this from basically cite high-frequency trading. I do feel that comes from the fact that physicists have a lot of friends who go on to do high-frequency trading. So it's a very often cited example, but it's there. If any of you have an idea of where unforgeability, privacy, and instant validation can bring value, do let me know. And tacit coordination. What's tacit coordination? Is the ability to coordinate decisions between non-communicating parties. The idea is that you have parties who are like sufficiently far apart that communication between them has a certain latency, which you don't want to suffer. And the idea is that you want to coordinate their decisions in a way that maximizes some global utility. Quantum mechanics basically allows you to do this better than classical. You can already do this with classical strategies, but you can prove that you can get better statistics with quantum mechanics. So if a 20% gain in something is valuable to you, might be useful. It's possible to achieve without quantum memories, but then you're limited by distance because then you're very vulnerable to photon loss. And then once you have quantum memories, you can start improving on this. Right, and so why did I bring this here? Kind of to seek feedback, also to start discussion, really. Ultimately, I'd like to see this as a living document rather than a static RFC, just to be clear. I am looking for problem domain experts, people who might have an idea about where these things might be useful. And I have quantum information experts are always needed for rigor. And I'm seeking interested people to just brainstorm applications on this. And my ideal outcome is to find applications worth investigating, and that can actually be tried on the prototype network that we're building in Europe, definitely at SURF. And yeah, thank you for your attention, and I'm open to questions now.
All right, thanks Wojtek for shortening your presentation a little. We are going to cut this off on time so that we make sure that Diego gets his time. Dean Bogdanovich, you're up first in the queue.
Yes, you mentioned that the networks, especially you said the entanglement networks will not happen without the QKD. I would say that the topologies that you're looking for, wide area networks, and the applications are quite a bit different than what will be used for the entanglement networks. Entanglement will be mainly a data center environment, versus your applications are more focused on the wide area network.
Sorry, can you repeat? Entanglement will be mostly.
So you mentioned that without doing research in the wide area quantum networks, the entanglement networks will not happen. It was one of your first slides. I think it was second or slide.
Yeah.
But those 2 slides are, sorry, those 2 networks topologies will be very different. One is entanglement networks are mainly focused on data center, building distributed QPU fabrics, where you're looking for some wide area network applications. And we know from classical networking, there are some significant differences between the wide area and the data center networks.
That's a good point. Probably should have qualified my answer. Indeed. Yes, I completely excluded in my head data center networks from that statement. Indeed, entanglement networks will evolve in data center networks completely on their own. I myself mostly concerned with applications in wide area networks. So indeed, yes, I agree with you. Thank you for that remark.
All right, any other quick questions? The queue had gotten locked, but I just unlocked it if anybody has anything else to say. Diego would be using his own time, so Diego can use as much time as he wants.
So I can speak for hours. No, simply when it's about this discussion of the live document, etc. For sure that we keep that as a live document is interesting, but this is something that has happened in other groups. Keeping an RFC, keeping a draft, even if it's not intended to become an RFC at the end, is something that can be easier for others to access. You go to the group description, you see documents, you see the draft, and from someone that is looking around, probably if you have this in a wiki or some other resource might be a little bit more difficult. Just we can keep it alive, and in every IETF meeting update the draft so the commoners can have access to it.
That's a good point. Thank you, Diego.
All right, and with that, I think we will thank Wojtek here and put Diego up on stage to talk about the actual draft. So we'll be moving from sort of researchy presentations into actual work for those of you who think of this is the only form of actual real work that gets done this week.
Thank you. So,
Dave
Sure.
Moran says the
Sure.
research is the real work.
I insist very much that we try to do in my team at least is applied research, and that's then that we believe that's the real work, because we look in the two directions and well, anyway. So this is an update of something that we started to work some time ago, which is this multiplane proposal for a quantum internet. And I have included 2 reminders because we meet from every 4 months or so. The idea is that it's not a set of protocols because things are not mature enough to be talking about dedicated protocols, etc., but about having a reference framework that can be used to support the analysis and how the different proposals fit and how we can fit them together into something that is close to the quantum internet. Think about it as something that is a first attempt to build the layer structure that started with the physical link, internet, etc. So then you can put there TCP, you can put there UDP, you can put there IP. That's basically the idea. So it's a little bit more complex than the typical layer function because we are talking about several, what we have identified, we are calling them stratums or strata. That's the plural in Latin. Different because you have several interactions there, and we're trying to apply first all the experience in the deployment of QKD infrastructures. Wojtek was mentioning that in Europe we are deploying EuroQCI, etc. In particular in Telefonica, we have a couple of rings that are interconnected, providing QKD right now, QKD services, and we are starting to play with general entanglement distribution and apply something that has been discussed inside the IETF as well, like, around the SDN concepts. And applying in particular an architecture that we consider is quite important. And finally, taking into account that everything goes to the cloud. And this is taking into account the implications of having everything virtual, though we are basing what we are doing on sound physical foundations. So the document has been around for more than 1 year, and the latest version that is highlighted there is about a much deeper discussion on network virtualization, how network virtualization is currently applied in QKD and will influence, or we believe will influence, the future quantum internet on the one hand. These two are connected when talking about the technology foundations and when talking about the concrete framework architecture proposal. And second is about making a more detailed analysis of what is the architecture that we're proposing. So the second reminder is that we're proposing is 3 strata. The idea is that we're assuming that you can put layers, but inside there things are much more complicated, basically because we have totally three different goals that have to be coordinated. One is the service. One is what you are intending to do. Distribution of keys in QKD, distribution computation in the case of what Rod was presenting, because I was not here, but I was watching you. Marvelous, Mítico. And we are talking about different services, and this is important because it's a way, the goals are different, and it's important to talk about that. Second is precisely how we propagate quantum signals and how we share quantum states, etc. And third, and is equally important, is the connectivity, pure connectivity. We need, up to now, we need, well, and I cannot imagine how we can avoid that. Not necessarily permanently, but we need physical, classical connection. We have a fiber that goes from A to B. Then we can have the entanglement and forget about the connection, but we need that. And that physical, we had to coordinate the three things. We had to coordinate at the service layer, at the service stratum, we had to coordinate the quantum stratum itself, and we need to coordinate the physical. And that's where we propose this architecture with these interactions. One of the main things that we have added in this version is the analysis of service units, which is the main concern of a service stratum. It's about a key, a particular key when we're talking about QKD. It's about you had to derive 128 bits of key. But what we're talking about share states, we're talking about identities, or tokens, like Wojtek was mentioning, and it's quite interesting. I have taken note of this because I had to make a review there and try to identify service units per each one of these elements. And that, well, basically, this is the base for essential network functionality. It's what we provide to the applications, what the network would provide to the applications. Typically think about the socket concept in TCP that provides an end-to-end connection that is like a direct pipe. When you throw bytes and you get bytes at the other side, is something similar. And what is important is that this is the base, the essential base for the addressing, routing, how you structure the information, everything. And that's the service unit needs to be, on the one hand, supported by equivalent units at the quantum forwarding, but not necessarily, and this is important, for right now the problems that we have is about how we reproduce a qubit here or an entangled state here on another point. But one single state is not especially useful. We need to group them. But we think that it's not necessary that there will be a packet of whatever the nature of the service stratum that is going to correspond to the same packet of qubits, if you like, at the quantum forwarding. But that corresponds to something that we have to analyze, and we plan to analyze in further versions. And finally, for sure, we need to, for building those service units, we have to rely again on the classical physical connectivity that is, well, we take it for granted, but is, at least in our experience, it's one of the great challenges whenever you want to build something that is, and don't forget about that, we're trying to establish the ways of operating and running and managing the networks in the future. And then it's about the QKD, the virtualization aspects. We have made an extensive analysis of how this has been applied in QKD and how this can be applied in QKD. For QKD right now, what people have basically is links. You are connecting two data centers with, well, not so cheap devices that allows you to encrypt data between those data centers and that have applications. We are found even interested customers. There are people that are paying currently for this, and that's fine. No, it's not fun. It's fine. It's fun as well, but it's fine. And but we have found that if we want to build a real network and the possibility of connecting in a certain moment point A with point B, or with point C, or with point D, or with all of them at the same time and share some service, we need something more. And we need authentication, authorization, and accounting. We need some degree of admission control depending on the capacity. We need mobility, we need monitoring, we need distributed management, etc. And the idea is that for this, we are relying very much on network virtualization in decoupling as much as we can the quantum forwarding stratum from the service management, so we can facilitate, for example, well, scaling the service elements or facilitating inter-domain communication that is essential if we want to talk about a network. And on the other hand, this virtualization is allowing us to simplify integration, to have a multi-device, multi-technology network that is providing a consistent service. This is something that we're starting to achieve. And something that is very important for us as well is about mixing real or physical and emulated environments. So we may see what happens when we have a network with a dozen links, physical links, as we have right now, and how would it look like if we extend it to, instead of a dozen links, have 120 links, and we have another order of magnitude, and we can play with it without spending the money. And what happens when you make the mix between what in QKD is called trusted nodes, that are things that make the forwarding at the service stratum, but they push the connection down, the service units down back, the quantum forwarding, and how we can think that trusted nodes like those that are not quantum repeaters by far, but act like they were, how we can make the network suitable for evolution. If we translate this into this experience in QKD, into what we think would be in the quantum internet, the idea is to, thinking that there is a direct application at the service stratum, because we are going to virtualize everything. Everything is going to be virtualized, support these interactions the same way we're doing in QKD. Leveraging what is right now a general trend in optical networking, which is this disaggregation idea that everything, you have physical elements that are fully controlled by software and can be attached and detached dynamically from different sources. And for us, it's considered a very much better integration with the service, so the service can control directly the connectivity dynamically. And third is about thinking that we have started some conversations with people that are working in building quantum repeaters, quantum memories, etc., on how we can provide some degree of software-based control of agents that are running on top of these memories and can interact and expose something that would be close to those service units at the level. We are analyzing how this mapping can take place, and planning for for the moment in which these repeaters are reasonably available to start thinking about the control and trying to define the interface for that. And the important thing is that the same patterns for simplifying integration will be applicable here. We will be talking about device diversity in quantum forwarding, which is something that we have more or less achieved in the case of QKD. Here is about analyzing this, mixing physical and emulated environments, and everything that is the same way we have trusted nodes that are service forwarders, how we could think about service forwarders in quantum repeaters. The catalog that Wojtek was mentioning is quite interesting in these terms, because we could start analyzing one of these applications that don't require necessarily of the quantum memories and starting to play with them. And just to finish, this is how the document is there. It's not that very long document. I would really appreciate if you have a look at it and make any comments or suggest any addition. But we plan to enhance the discussion on virtualization, because it's something that is, I believe, is one of the main roads that we need to go on for a proper operation of the whole infrastructure. Let me say, we are not trying to solve the problem of how you make the actual forwarding of the physical links. We are, I am a physicist in my young days. I earned a degree in physics, but I have forgotten almost everything on it, and I am more a software guy than anything else, and we are very much focused on this and how we organize all these to be operated and properly managed. We want to generalize and analyze in detail the service unit concept. I must say that the former presentations, I was taking notes because there are a couple of things that we probably would be reflecting here. And I mean in all of them, so it's something that we will be talking about later on. And we want to see whether even, I'm not sure if for the hackathon in Madrid we will have something that would be suitable to be shown or shared, but it's about demonstrating this idea of the integration. I will try to, since you are going to be at home or at my home, and try to show some degree of integration with what we have now running there. Well, in terms of formal things around the draft, is about the security considerations. We have not opened this that can yet. We will work on the security considerations, and in a certain moment, if our most appreciated chairs think of this could be considered the adoption, so we change the name and they just have an IETF in the title. And that's all from my side. Yes.
Thanks, Diego. Dean Bogdanovich, and my apologies if I'm mispronouncing your name
That's fine.
first.
Dejan Bogdanovich, all good. My favorite slippery slope, the soapbox, network management. So in the IETF, we are dealing with some 20 plus years concepts of network management that have been created in the mid-90s, and we are still having many things backwards. If we are planning to do a network support infrastructure for the quantum networks, let's think about what would be the right architecture and what would be the right concepts to be used, and let's not make the mistakes that we did in the classical networks. So that would be really my first thing to take into the consideration, and seeing what is the best way to make quantum environments from a connectivity point of view easier to operate. So that would be, from my perspective, the number one thing, and trying to learn what are the operational requirements for such hybrid environments before we start picking up some of the, in my opinion, outdated concepts from the classical world.
I think Dean's encouraging us to make new mistakes.
Yes, take a risk. I'm definitely saying take a risk and see it, because we can learn a lot from the mistakes that we did in the classical networking. And if you look out into the concepts that are being used by certain groups on network management outside of the IETF, they have some much better ideas than what we are still nurturing in the IETF. So look around before starting to adopt what is within the IETF, which is, from advanced point of view, already outdated and hasn't been adopted by the service providers. And your employer is running into the problems by trying to adopt the IETF standards, and then you're mixing a few things up and you're running into your own problems as well. So you could share some of those experiences.
Well, I mean, what we're trying to provide here is precisely a way of evaluating the different proposals, new or old, and taking into account, but taking into account, and in that respect, we're trying to be realistic, that for this to become operational or suitable to be operated, something that you have to do is to converge to what is the current practices, even if they're wrong, but some of the current practices in operation, and try to go, let's say, in parallel with it. That's something that even may imply making new mistakes and mixing them with the old mistakes. But in some cases, you have to live with what you have, and it's difficult. What doesn't mean that some of the concepts here cannot be used to improve them. Just to give you an example, something that we are now working in is about, I mentioned this AAI and this admission control. We have a prototype running right now on part of the Matthew CI, the network that we have in Madrid. Right now we are using the same OAuth tokens that are being used all over the place, but in our to-do list is to start playing with the idea of these unforgettable tokens that Wojtek was mentioning, so we can use something that is new, that then could be exported elsewhere. We want to start, and for sure, this is good to learn from the past, and we are trying to provide the framework before we have a big network already deployed. And well, let's play with this while we are doing the real thing, and let's think about what we can, what lessons we can derive. Yeah.
Any other questions, comments?
It's Michael from Huawei. I went to the mobile conference last week, and I have talked with the Telefonica guys. I know that our Telefonica have already launched some commercial offerings on the IoT scenario and the VPN scenario in some island, which is based on the PQC.
Yeah.
Yeah, and also in some meetings, the TO2 have the cooperation with AWS on some QKD or this. And it means that we also have the QKD experience and research. And I just have a question about, in your opinion, about the network security, the PQC and QKD, what's the relationship between this, and what's the situation for them?
We love each other. Not seriously. No, seriously. What we are trying to do is that we are service providers. We are to provide service to our customers, and this is, we live on it. So what we are trying to do is try to have a very, very pragmatic approach in that sense. People is concerned about the quantum attacks to network security, and so we are trying to provide solutions. And for example, all this that you mentioned of PQC on the Mobile World Congress is something that is happening right now because there is a demand, but at the same time, we are experimenting with QKD, and we have customers that are more interested in QKD, and what we are trying to do is trying to identify quantum secure, safe services that are not necessarily only QKD. QKD is expensive, it's difficult to maintain, etc. And the idea, what we are trying to do is in general, is about providing quantum security services, whether QKD or others, on the one hand. For example, we are extremely interested on these matters regarding oblivious computation. We believe it has a very, very interesting path to work, and we are making some experiments. We made some experiments on the analysis of genome between a university in Portugal and another one in Madrid, about trying to demonstrate that oblivious computation can happen. And second, when it comes to PQC and QKD, our idea, if we can, and we are working on that, is trying to provide a uniform access to key distribution, whatever the solution is. Among other things, because we believe that this requirement of crypto agility that you hear once and again when talking about PQC can be extended to a combination of any quantum safe crypto technology. And the idea is to have something that warrants crypto agility, and you don't see whether it's, that depends on your concerns, but you can buy or hire from us a service of quantum safe key distribution, and then we will take care whether it's PQC or QKD, and according to the terms of and your needs. We don't believe that there is something in this a one and only solution that will be applicable everywhere, because experience shows that normally is not the case.
Thank you. Thanks a lot.
All right, I think we need to cut it off there. We're running up close to the end of our time here, unless somebody has any quick final comments or questions. All right, Diego, thanks. Let's push this forward on the mailing list. All right, final comments. Let's see. One final comment. Over the last several years, QIRG has usually met face-to-face in March and November, and skipped the July meeting, but just talking to people in the halls, there seems to be substantial sentiment for meeting in Madrid in July. So there's a very good chance that there will be a QIRG meeting in July. If you have opinions, either yay or nay, speak to the chairs. We're happy to discuss it with you. Wojtek, anything else?
I guess only that we should, I guess more interaction can happen if we move some of the stuff that we've presented onto the list and give people time. I guess that's one of my takeaways from today. But we'll take it up on the list.
All right, we'll see you all in the hallways. And as I sort of said in an aside at one point, some of us are going to go to lunch, those of you who are here face to face. So if anybody wants to join us, it's just informal. We're going to walk someplace nearby and go to lunch if you want to discuss this more. Thank you all.
Wojtek, thank you and goodbye. Rodney, good to meet you.
Nice to meet you too, Oscar.